La la la. Okay, good. I'll begin. Dear Heavenly Father, we thank you for this day. I thank you again for these students. Just pray that you help us to understand a little bit more about momentum today. In your name I pray, Lord Jesus. Amen. So I'll start with the ballistic pendulum example. So you have some real-world experience with this, I think. And here's, roughly speaking, a picture of the thing. Yeah, a pendulum. And I'll draw the end. Here's what happened. Here's the end, sort of the end point of it. And then down here. All right, so before we have some little bullet, say with mass little m, all right, and it has some initial velocity v naught, all right? Then there's this pendulum sitting here. Maybe it's like a lump of clay or something. It has mass big M, so like m with feet, let's say. And then it goes into the clay, all right, and it embeds there. So if I could draw this at just a slight time later, right? Very, very slight time later, okay? It's something like this, right? Now you have m plus m together, all right? And then they swing up here, up to there, right? Still have the bullet in there. I'll make it green. All right, and let's suppose that that swing goes up to a height h. So then the question, of course, is, and oh, I should also tell you the length of the, the length here of this is L. All right. The question, of course, then is how high does it swing, right? Now, I personally had this question, this very question, right, on my introductory, well, not introductory, junior level mechanics. The first test was on. This was on there. I mean, pretty much verbatim what I just told you. Find the height, given the initial velocity of the bullet is v naught, and it sticks to the other one and it swings up, And so here's what I did. I said, okay, I got this. 1/2. Oops. I said 1/2 m v naught squared, right? That's the initial kinetic energy. And then what's the final potential energy is what? It's big M plus little m, all right? GH. So therefore H is equal to, what is it equal to? Well, 1/2 m v naught squared divided by m plus little m times g. And I was like, cool. Now I can go spend my time on other problems. Got that. Done. Nailed that. I felt good about it. Felt good. So I come out of the test and talking to my friend, who I refer to as Somber Paul, not to be confused with Crazy Paul. Crazy Paul did not earn many points on classical mechanics tests. He passed, but Somber Paul, on the other hand, he was a force in classical mechanics, because that was the semester he dropped his mechanical engineering double major, and like a phoenix rising from the ashes, his true nature was revealed. He towered over the rest of us like we were peons in that class. He was a destroyer of worlds in classical mechanics. I mean, he took the graduate classical mechanics, and like there was only like one person who could even like come close to beating him, and that guy was a Russian. So, yeah, he was a Russian, which probably means he's already taken the classical mechanics somewhere else. No, Paul was really good. He got a PhD in physics, as it turns out, from UVA. A few years later. Anyway, and then Paul. So I was talking to Paul. I'm like, yes, I'm very happy about that question. Like, I just, and Paul's like, yeah, you just conserve momentum and then conserve energy. And I said, you what? I said, you conserve momentum, then conserve energy. And then I said, oh, yes, momentum is conserved. That is true. And that is what I did not do. And that is why what I wrote on the board is not a real solution. Even though it was my solution. I got half credit. All right, anyway, so no. Here's the thing. Energy is not conserved in this process. Yes, sir?
How do you know with the height what reference point to measure the height from?
You can assume the box is infinitely small. That's beside the point. Like, we could measure the height relative to the center of mass of the box before and after. That's probably the most reasonable thing to do. So I'm saying it's gone height h up to relative to where it was before. So we're measuring height in the same sense in both cases. You could measure height on the basis of the top of the box or the bottom of the box. Now, here, if it's bothering you, I think I know what to do. Now, whatever ambiguity you're thinking about is gone, right? I mean, that's not the point of the problem. Okay, so the point here, though, is I can't just conserve energy because the process of this bullet hitting the mass and embedding in it is not a conservative process. That's an inelastic collision. So what I have to do is I have to, there's really three moments of time here. There's the initial moment, there's the event one, which is the bullet is stuck in the, in the clay, and it's just started to go up. The initial speed of which, well, let's say, is v1, all right? And then there, of course, is the third event, which is over here, right? So going from zero, from event, going from the initial, going from 0 to 1, we conserve momentum. And the conservation of momentum there looks like this. It looks like little m v naught is equal to little m plus big M v1. My wrong solution essentially assumes that v1 is equal to v naught, and that's just not the case. Something like that, anyway. All right, so that's the first thing. At least the parade of garbage cans hasn't started yet. See here. It'd be a different kind of I guess if Oscar the Grouch had gotten as big as Mickey, maybe that's how that park would close. It's like every night you'd walk out, you'd see all the custodians taking the trash cans towards the front gate. You'd be stuck in crowds watching them with nervous excitement as they push the trash cans down the street. It'd be amazing. Sorry, if you've ever been to Disney World and made the mistake of staying till the final moment, you get stuck in this crowd of watching these people with lights, and if you're tired, it's very frustrating. There's no way around it. It's a juggernaut. That's a word we don't use enough. Juggernaut. All right. 0, 1, 3. Interesting. Let's make that a 2. Okay, so going from 1 to 2, we conserve energy. Okay. In fact, momentum is not conserved going from 1 to 2. There's an external force at play going from 1 to 2. What is the external force? Gravity, right? Yeah. In fact, the momentum is dropping all the way to 0 at the zenith of the swing, and that's not really interesting. I mean, but what is interesting is that energy is conserved in the upswing after the collision, right? By the way, momentum is conserved in the collision because it happens over a short instance of time. There's no vertical motion in that collision. There's no time even for gravity to change the momentum during that collision process. Okay, getting back to the point. So now I can say 1/2 m plus m v1 squared is equal to the final. My final energy formula wasn't wrong. It's just my equating that to 1/2 m v naught squared was wrong in my original solution. Now I have to solve these two equations and however many unknowns. See, how do I do that? Yeah, solve for v1's not a bad idea. So I'll do that. I'm gonna be a little bit, well, yeah, fine, I'll do that. Yeah. Okay, fine. I don't know, I always kind of think a little bit about non-standard substitutions. Like I might try to like work with m plus m times v1 if that gets me something, but it'll probably just get me confused today, so let's solve for v1. All right. Solve for v1. There it is. Plug it into the second equation. Like so. 1/2 m plus m squared v naught squared divided by m plus big M squared is equal to m plus big M. I mean m plus big M plus little m, gh. Now I got to solve for h. H is equal to then. Looks like we can. Yeah, cancel out the m plus m. Oh man, is green marker cap messing with me. Let's see here. Okay, so h is equal to m squared v naught squared divided by twice little m plus big M quantity squared g. So whenever I do something like this, especially when I'm still recovering from some mind-altering sickness, it's a good idea to check your work, especially check units. So you notice you got units of mass squared in the numerator and the denominator. That's good. Kilograms squared cancels. Upstairs I've got like a meters squared per second squared from the velocity squared, right? And then I'm dividing by g, which has units of meters per second squared. So the second squareds cancel, and we're left with meters squared over meters, which is meters, which is good. And there's how you derive that. Now I think your lab report has extra stuff in terms of the angle of the upswing and stuff, right? But this is the heart of it. Conserve momentum and conserve energy, and that's it. There's lots of ways of twisting this problem a little bit, right? Like there's another problem I've seen in the homework. I don't know if it's in your homework, but I've seen it in homework. I can't remember. The years all kind of blend together in my mind. But there's another version of this problem where the bullet goes through, but loses some speed, right? And then the thing swings up. I suppose there's another version where the bullet bounces back and this thing swings up. I mean, there's various ways you could twist this a bit. But in any event, all of those, you conserve momentum in the event of the bullet colliding with the pendulum, and then you use conservation of energy to see how far it goes up, and that's how you do it. Any questions? Yep. Momentum is conserved in collisions. Momentum is also conserved on a system if the net force on the system is 0. But if the net external force, of course, and the system is not 0, momentum need not be conserved. For example, the exploding cat thing we did, right? So projectile motion up to the top. Well, the y momentum has gone from non-zero to 0 at the zenith of the flight. But on the flip side, the x momentum is conserved right up until the point of the, well, no, still after the explosion. I mean, momentum is still conserved. But yeah, that's a deeper question. Is there an example in physics, set aside classical mechanics, where momentum is not conserved? I don't know of one. Even light has momentum, even though it doesn't have mass. So this notion of momentum extends past just this MV stuff we're doing. It's more fundamental than the concept of a force.
How does light have momentum?
Yeah, that's a good question.
Does it have an answer to it?
What's that?
Does it only have an answer to it?
I think so. Yeah. All right, let's see. For light, I don't know if I'm supposed to tell you guys this right now, but how's it go? Energy is equal to the momentum times the speed of light, if I remember right. Energy is also equal to the Planck's constant times the frequency. And what else is that equal to? How's it go? Wavelength? How's wavelength relate? Say again? Planck's constant.
HC over lambda.
Oh, HC over. I'm sorry. Right. Exactly. That makes sense, of course, because lambda. Well, let's see here. I'm an idiot. F is equal to C lambda, right? C
over lambda.
Okay, that makes sense. Yes. The frequency of light is the speed of light divided by the wavelength of light. So if you take the how many meters per second it goes, and you divide by how many meters a particular cycle of light goes, that gives you the number of cycles per second. Or its frequency, it's hertz. But this is the momentum. Momentum for light is related. So I guess you can divide this by c, and you see you got momentum as what? Yeah. So the smaller the wavelength, the greater the momentum. Right. So like, for example, the momentum of a radio wave, whatever. The momentum of a gamma ray, it's something. Of course, the source of the Hulk's power. My children have been very disturbed. This TV Hulk, it's small. It's the size of an ordinary man. It's confusing to them. They're like, that's not the Hulk. You know what I'm talking about? You guys ever seen like the 1970s Hulk? They're starting to play it on the Me TV. So my kids have seen a random episode or two. They're like, what? That's not the Hulk. Because, he's like, there was this episode where I happened to see last week. He is having trouble getting out of quicksand. It's like the Incredible Hulk is having trouble getting out of quicksand. If you've watched any of the recent Marvel movies, does this make sense? What's that?
How are you going to push yourself out if each time you push?
No, he would just like eat the right now he would eat the quicksand, yeah. Yeah, I don't know. It's kind of the Incredible Hulk from the 70s. It's kind of quaint. I don't know. It's touching. It's much more emotion and acting, and the music is very nice. I digress. But yeah, I don't know. So this is an experimentally determined fact. I don't know how to explain that. I'm trying to think. I mean, there's a theory of light as a wave, and waves do also carry momentum. And so, and yet light doesn't have mass for reasons I'll explain more. Well, I'm not sure I'll really explain it, but I will give you more details about that in a few weeks. Okay, I have set aside a few lectures in this semester to talk about special relativity. So they'll be a little bit different than some semesters I've taught this. I always try to talk a little bit about it, but I really tried to set aside a few days so we can actually do it a little bit better this time. Because usually there's a few of you who are actually interested in it, and so I should actually oblige you because we don't have a physics major here, so where else are you going to hear about it? You know? I guess you could go to Wikipedia. But, all right, so. One-dimensional. Actually, forget about one-dimensional. Let's just talk about collisions.
Are we not doing special relativity today?
No. You don't want me to even try anything. No. 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 You have a test, don't you? Sometime soon? Yes? Tuesday, yeah. So we need to wrap this up so you guys have time for your homework questions. So a two-body collision, we can generically cast like this, right? It's you have something like, let's say MA. MA, listen to me. This marker is useless. Two bodies, so I got like MA, all right. It's got an initial velocity, VA1. I've got MB. It's got an initial velocity, VB1. And then, bang, boom, whatever. You've seen Batman, you know what words to put there. And then afterwards, they come out, and they've got different velocities. And I'm drawing this two-dimensionally, but it's really three-dimensional, okay? And I'm debating whether or not I need to put commas there. This diagram is really just for heuristic purposes. I wouldn't read too much into the directions I'm putting on these arrows, okay? Okay, so collision. So what do we have? We have that momentum, right, is conserved. What does that look like? It looks like MAVA1 plus MB is equal to MAVA2 plus MBVB2, right? Now here's my question, is what if we change the frame of reference? So I've told you momentum is conserved, right? That assumes there's some frame of reference, right? If you think back to the arguments that I made, I said assume there's an inertial frame of reference that's sitting there immobile, and then we measured relative to that frame of reference the position of all these different masses. We differentiated, applied Newton's laws, did some arguments, right? That was all with respect to that one fixed inertial frame. Suppose you take a different frame of reference. What might be an interesting one to think about? There's a couple different choices. I mean, you could look at the let's see here. You could look at the center of mass frame of reference, right? You could look at the center of mass of MA and MB and use that as your origin and measure velocities relative to that, for example. It's one thing you could do. Here's something a little bit easier to think about for our current purposes. You could look at the frame of reference in which B is at rest. What would that look like? So I've got, let's see, I'm given X, Y, Z coordinates, right? I want to find X bar, Y bar, Z bar coordinates for which be at rest. It's not hard, guys. All you do is just imagine attaching a little co-moving coordinate system here like this, and just make it go in the VB1 direction. In other words, let's see here, how would that go? And we can just pick a particular instant of time where the MB is at, and just say that's the that's where the origin is at, and kind of go from there. So I think the specific formulas would be something like x bar, y bar, z bar is equal to, I don't know, wherever that thing is. Oh, I don't really care about the positions too much. If you don't mind, I'm just going to go straight to the velocity. Velocity transformation. So v relative to b's initial co-moving frame. In other words, I'm saying imagine a frame of reference which moves just with the b mass, just like that. All right.
It's like
Co-moving. It moves along with the mass. Yeah. What's the how does that relate to the other velocity? Well, you take the velocity relative to the given frame, which we talked about already. In other words, that's the frame that we just assumed existed and we were doing the calculations for in the previous classes, and we're always assuming is there, right? You take that velocity and you just subtract what? You subtract VB1. Now, if you want, you could integrate this to find the relation between the position vector relative to the co-moving frame and the position vector with respect to the fixed inertial frame that we're assuming exists from the outset. VB1, this is just a constant vector, right? Because this mass there's no force, it's just constant velocity motion, right, until the collision. So that's just a constant vector. And there it is. I mean, so, for example, what's the velocity of B with respect to its co-moving frame? That's right. Now, this is like a lot of writing, and it's kind of annoying, so can you think of a different symbol we could use for this to make our life a little bit easier? G-rel? Okay, sure. I'll take it. Actually, no, for other reasons. How about, I want to use prime. Could you guys let me use prime with the understanding that we don't mean differentiation? Let's use prime for a label. So that would be VB prime. So how about up here? If momentum is conserved, right, in the fixed inertial frame, is it also conserved in the co-moving frame for B? In fact, it is, right? If you just think about it mathematically, all you're doing is you're just subtracting VB1 from both sides. So you subtract VB1 times MA to put primes here and here, and subtract VB1 times MB from both sides to get primes here and here. So you can easily see that we can put primes on this equation in the sense that momentum is also conserved in the co-moving frame. Of course, in the co-moving frame, we also know what? VB, this doesn't have to be B. What am I? I'm an idiot. This is the velocity of whatever. But in particular, VB1 prime is what? VB1, right, minus VB1, which is 0. All right. My point in this whole discussion is very simple. No loss of generality is obtained by assuming one of your particles is at rest to start with. See, because we can always take the problem you're given, right? Maybe both of the particles are moving, and you can change coordinates to a coordinate system where one of the particles is at rest and only the other one's moving. Momentum is still conserved in that new inertially related frame, and the problem may be simpler to solve there. This is this you probably will not need to use this idea to solve any of your homework problems or anything, but it is a good thing to know about. I mean, if I was to write homework for this course and not use book homework, then it would be different. Yes.
So it's like the difference between like watching like say like two planets collide and then like being on a planet and watching something collide with it.
Right, right. You know, we sometimes are very critical of early Christians because they, bought into this idea that the earth was at the center of everything. But kind of take a step back and just imagine yourself without the knowledge you have. It's not so crazy. And does the sun rise in the east and set in the west? From our earth frame of reference, that is still a true thing. It's only from the absolute reference frame of like the interstellar, if you can take yourself off the earth and look at it from, a satellite sitting out there or just some fixed point. Even that's not a fixed point, right? Some sort of co-moving point with the Milky Way galaxy, which is, by the way, going very, very fast through the larger galactic whatever. I mean, everything's moving. So, anyway, if you could put yourself at a point which isn't moving relative to the Milky Way, but is kind of fixed with respect to the motion of the Earth and the Sun, then, of course, you'd see that this, Earth is revolving around the Sun, right? But it is still true from our reference frame that the sun is revolving around us. That's not wrong. It's just from a different reference frame. But be careful who you try to argue that with.
I'm gonna try convincing you earlier today that the earth is flat.
Well, no, it's not. You're right. Okay. Sorry. So if we could, I'm sorry, I'll behave. So what I'm really trying to get at here is to explain to you why the starting point of this derivation isn't so crazy. What I want to do right now is to show you if we have two bodies, right, one in a one-dimensional system, all right, so they're like stuck on a plane without friction. There's no friction in the plane. Maybe like two billiard balls or something. They're stuck in a, I don't know, just in a one-dimensional thing. Maybe it's like a, I don't know, like a pipe that is very, very slippery. So that's not a very, but these billiard balls can, when they collide, they don't have to, well, I do allow the possibility that they pass through each other. So that's not, it's, or they bounce, and then it's easier to understand. But the point here is, I've got two balls, let's see here, say MA and MB, right? And that's before, and then after. One-dimensional, no friction, all about the collision, all right? Now my point to you in all this discussion about frames of reference and such is really just, it is, that center of, there's more to say about that center of mass frame. I'll have to talk about that some other day. Not relevant so much to this part of the course, but there's something to talk about there. But before, my point is, without loss of generality, I can assume that one of these balls is at rest. So let's say that B is at rest. Let's just look at everything from that frame of reference. That's not a bad thing. So this has velocity v then. And then I can just say that this has velocity va, and this has velocity vb, And I don't need those stupid subscripts, which is nice because I'm about to do about a half-page algebra. And if I had to do it with the subscripts, it would get really, really old really, really fast. All right? Suppose that the collision is elastic. Is there anything special that's true? Well, elastic means that their kinetic energy is conserved. So kinetic energy before equals to kinetic energy after. Right? What else? But the collision, so we have kinetic energy before equals kinetic energy after. What else do we have? It's a collision, right? Momentum is conserved. So we also know what? Ma V is equal to Ma Va plus Mb Vb. So what's the relation between, what do we get here? Let's try to work it out. So we have 1/2. You might wonder what we're working towards, right? So 1/2 m v squared is equal to 1/2 ma va squared plus 1/2 mb vb squared. We can cancel the halves, right? Now my goal, I happen to know, and you might discover this just from working specific examples, but the interesting thing that turns out to be the case is that the relative velocity which we could define as VB minus VA is equal to VB, so here's, let's say, after, is also equal to VB naught minus VA naught before, but not the same. It's minus that. That's the result we want to prove. Now, VB minus VA that's just what I have used as the labels. Here, in my current labeling, what's VA naught? Right, and VA naught is, V, I'm sorry, what's VB naught? 0, right? So this is just actually V, right? So my goal, right? Our mission, if we should choose to accept it. If you don't mind, I'm going to erase these halves. You watching? We want to solve these equations here. I wish to solve these and show that V is equal to VB minus VA.
Why did you get rid of the squares?
They were never there. That's momentum conservation. These are different equations.
Oh.
Yeah, no, right? But that's not a bad idea. How do we put the squares there? How about square it, right? So this is ma squared v squared, right? Is equal to what? ma va plus mb vb quantity squared, right? Or if we divide that, we've got ma v squared is equal to, well, let's see, how can I look at this? Oh, I should actually square that out. So if we square this out, what do we get? We get like ma squared va squared plus 2 ma mb va vb plus mb vb squared, mbb squared vb squared, right? What's that?
There's just so many things.
I couldn't hear you. What?
You said there's so many things.
Oh, well, yeah, I would guess so. So we need to eliminate, what do we don't, let's see here. I want VB minus VA, right? I'm trying to remember how I did this. I mean, I could look in the notes, but that seems like cheating. Well, one path forward is to, I see how to solve for v squared, but I'm not sure I want to do that. Oh, I'm an idiot. What I should have done, yeah, I kind of agree with Travis. There's so many M's, and what I should do before I square it is I should divide by MA, right? If we divide by MA, what do we have? Right? And then square that. That's a little bit neater, right? Now I can plug that, right? And let's take the kinetic energy equation and simplify it a little bit. That's really v squared equals to what? VA squared, right? Plus MB over MA VB squared. Right? So now I got v squared, I got v squared. So I can equate these. What does this give me? V squared equals v squared, right? So square this out. What do we got? We've got VA squared plus twice MB over MA VA VB plus MB squared over MA squared VB squared. Anything nice happen here? Can you guys see how to simplify this at all? In other words, we have this is equal to that. Well, something jumps out at me immediately. We can subtract VA squared from both sides, right? That's out of the picture. What do we have then? We have MB over MA VB squared minus 2MB over MA VA VB equals to what? Equals to 0. Oh, I'm sorry. I've still got that what? Plus MB over MA MB squared over MA squared VB squared, right? That's also, I guess, right. Well, we have VB, this is equal to 0, so that's, you notice I got VB squared on two terms, right? So I got VB squared times what? What should I do to this equation? There's a lot, again, going back to Travis's comment, there's lots of m's here. Let's get rid of some of them.
Multiply
multiply by MA and divide by MB. How about that, right? So we've got a surplus fraction, MB over MA, MB over MA, MB over MA everywhere. Two of them here. That's the only one that's going to survive after we divide by that fraction, right? So this cleans up a little bit. This is VB squared minus 2 VA VB, right? And then what? Minus MB over MA VB equal to 0. Yeah, VB squared again. Oh, now if VB, okay, so I guess if VB is equal to 0, if VB is equal to 0, then what's the deal? I think if VB is equal to 0, we can come back and solve these equations easier, right? Like if VB is equal to 0, then this just tells you V is equal to VA, right? And likewise up here, you'll end up with V squared equals VA squared. So like if VB is 0, these equations we can just solve through just direct. It's obvious. So we can justly assume that VB is not 0, right? If VB is not 0, then we can divide by it. And so we get what? We get VB minus twice VA minus MB over MA VB. So finally, I get VB times 1 minus MB over MA is equal to 2 times VA. Or in other words, VB is what? Two divided by 1 minus MB over MA VA. So see, now I have a relation between VB and VA. What can I do? My suggestion would be then we can take that, right, and plug it back into one of these guys. Which one should we do? I think, given a choice between plugging into something quadratic and plugging into something linear, we should choose the linear one, right? Yeah, I think so. So this gives us actually what? MA, and which one do we, I want to keep the V. And let's see here. What do I get if I put in well, anyway. Sorry, I'm easily distracted. MAVA, and I'd solve for VB, right? So put that in. Plus MB times what? Twice VA over 1 minus MB over MA. Does that simplify? I suppose we can divide this by MA. We get V is equal to VA plus 2 MB VA divided by, well, MA minus MB. Oh, I probably also have to use the kinetic energy equation again. Oh. I'm going to put you guys out of your suffering. Oh no! Sorry. See, if I'm well and actually thinking clearly, this doesn't take that long. It's not that bad, really. But if you, I mean, you can solve these equations. If you solve them with efficiency and clarity, they're not that bad. But if you don't, well, that's today. In a given year, there's about a 50-50 chance I'll do this nicely. Every other year I do it nicely. You're on an off year. Ah! No! Who did that? I blame you. Okay, it's not really reasonable. Come on. See, I want to finish this silliness because there's something more interesting to show you. Have you guys ever played billiards much? I mean, pool? If you do it right, what happens when you hit, if you hit a ball that's just at I mean, well, we don't usually play dynamic pool, right? I mean, like typically you wait till the balls have like settled and then you take the next turn, right? Unless you're very impatient. So if you have a pool ball just sitting there, right? And by the way, they all have equal mass, right? And then you have another one, right? And it comes in and you hit it with a cue stick or whatever, or hit it with velocity v, right? Collide. And then afterwards, you know, that one goes this way, this one goes that way. Right? Say, we call this 1, call this 2, just to give them a label. So, you know, here's where they collided. It's an elastic collision, all right, to a very good approximation. What's the angle between those lines? (90°) is right. We can derive that.
But not always.
What's that?
Not always. Maybe hit the ball almost straight on. And both go off this way.
If you hit it dead on, that's right. If you hit it dead on, one stops, the other one goes. Yeah.
It depends.
There's also spin, which muddies this. We're ignoring spin. Can somebody hit one of the lights? Thanks. Oh, fine, we'll come back to that. That's an actual example. They don't want to muddy the discussion with numbers just yet. Sorry. So we've been trying to solve this. MAV equals MAVA plus MBVB, and this, right? We've been trying to solve this. Well, apparently you can show, sorry, MVA is equal to MA minus MB over this MA plus MB times V, and you can show VB is equal to that in terms of V. So from these, then you can show that VB is equal to V plus VA, hence V is equal to VB minus VA. This is the velocity of A minus the velocity of B before the collision. This is minus the velocity of A minus the velocity of B after the collision. But by the change of reference frame idea I told you before, that's completely general. I mean, you can always move to the frame where one of them is at rest to start with. So the fact that this works in the situation one of them is at rest to start with suffices to show that this is always true. That's the argument. So like, before I get into the why that's true again, if I have an elastic collision, if I have mass 1, 10 meters per second, if I have mass 2, 3 meters per second, right? Elastic collision, elastically collide. And afterwards, I tell you that M2 is going 20 meters per second. Well, what's the velocity of M1? Actually, let me tell you what. Let me make up an example which is actually probably reasonable. How about 12? I'm not sure 20 is even possible. Yeah. What if that's an elastic collision, what would the velocity of M1 be? In what direction? So here we do V1 minus V2 before is equal to, this is before, minus V1F minus V2F. That's this theorem. So let's see here. V1 before was 10 minus 3. Well, not minus 3, but plus 3, because it's left. And that should be equal to minus V1F plus what? Plus 12. So V1F would be minus 1. In other words, 1 meter per second to the left. That's in this very nice special case, but I think it's an important special case to know about. So, sorry I've spent so much time on it. Let me finish since we started it. Here's the math. So what I do, I always started out right. Oh, I solved the wrong one. Well, didn't I do that? Yeah, I did that. And I did that. Yeah, I had that before. I solved for VB. Oh, solved for VB. I didn't do that. Doing that gets me to here. Oh, apparently I should have plugged into kinetic energy. That was a bad move. Sounded easier, but led us to nowhere. And then I solved for, difference of perfect squares. Oh, but that's nice because you get one of these and one of those, and then you can cancel off this guy and one of these guys. And that gets you there, which gets you that, which gets you rearranging, collecting all the V terms together and multiplying by MB. That gets us to this relation. And then I plug that into momentum conservation, I think. Yeah. And gets that the other one for VB. And then if I subtract this and that, I've got the same denominator, but the numerator works out to the numerator works out to minus MA minus MB. So it's MA plus MB and then minus MA plus MB upstairs, which finally gives us this relation. The point of all this, all right, guys, is if I tell you a one-dimensional collision is elastic, that's a very simplifying statement because you have this like pretty non-trivial theorem to work with and you can use this relation and life is easy. I've almost obligated myself now to put one on the test, right? I've spent so much time on it. I'm sorry about that. But I don't have to?
Wait, with the last one?
You don't want this problem on the test?